we can draw the shear force diagram from a bending moment diagram. So what we do is cut two segments of the beam just after and before the support, and just after the support here, and take a free body of those segments. Well, we know that at a pin there's going to be a shear force which we assume points upwards by our initial positive convention, which I'll draw here for your reference. And at a pin we have zero bending moment, and we'll call this shear force A. And at the roller we take this side of the convention, so we assume the shear force acts downwards, and here we have a hogging moment, and as we know, hogging moments cause tension on the top of the beam, and this hogging moment has a magnitude of 1.5 kilonewton meters. So on this 2 meter long segment there's also a point load of 2 kilonewtons acting on it. Now on this segment we also have a shear force, so I'll call this one VB1 and this shear force VB2, and we have a hogging moment which is negative, so it causes tension in the top of the beam, and that's the same hogging moment of 1.5 kilonewton meters. And at the overhang we have a zero shear force and zero bending moment, and this segment also has a uniformly distributed load acting on it, which has a magnitude of 3 kilonewton per meter, and the segment has a length of 1 meter. Now if we take equilibrium of the first segment, so we'll take moments about support B, with anti-clockwise being positive, so that gives minus shear force A by the moment arm of 2 meters, plus 2 kilonewtons by the moment arm of 1 meter, and then minus the hogging moment, and that's equal to 0. So the shear force at A is equal to 0.25 kilonewtons. And a positive shear force diagram is drawn on the top of the beam. And here we know the shear force is constant because there's a point load acting on this segment. And if you take a vertical equilibrium of forces for this first segment, with upwards being positive, we have the shear force at A minus a 2 kilonewton point load minus VB1 is 0. So that gives VB1 is minus 1.75 kilonewtons. So as expected, due to this 2 kilonewton jump, we have a shear force of minus 1.75 kilonewtons. And that's constant on this segment because it has a point load acting on it. Now if we take an equilibrium of moments about the overhang, with counterclockwise being positive by convention, we have minus VB2 multiplied by the moment arm, and the hogging moment here is anti-clockwise, so we have plus 1.5 kilonewton meters, and then plus a uniformly distributed load by 1 meter gives the resultant, and then by 1/2 is the lever arm, and that's equal to 0. And solving for VB2, we obtain 3 kilonewtons. So positive 3 kilonewtons is drawn on the top of this beam. And if you assume there's a shear force on the overhang, you can verify that by vertical equilibrium of forces, that shear force is 0. And the shear force diagram is linear on this portion of the beam because there's a uniformly distributed load. And you can also verify that this reaction here is 4.75 kilonewtons, which is equal to the jump in the shear force across the support. Please subscribe, like and comment to help me reach more students.